This video is going to look at practice 1, so 3 graphs of parametric equations from your parametric equations day 2 notes. So question 1 shows 2 parametric equations defined using trig functions. Right, we have that x equals cosine of t and y equals 4 sine of t on the interval 0 to 2 pi, including 0 but excluding 2 pi. And here I'm going to choose to explore the second option that we covered in the examples above. So instead of making a table, I'm going to go ahead and write a rectangular equation relating x and y using these 2 statements. So the first one, there's not much to it. We can just kind of look at this again as x equals cosine of t. There's no coefficient to divide over. And as a reminder, what I'm doing is I'm trying to get to a point where I can use the Pythagorean identity of sine squared of an angle plus cosine squared of that same angle is simply equal to 1. Okay, so again, wanting the trig function squared. So to accomplish that, we'll go ahead and square both sides of this equation here, and that will give us that x squared is equal to cosine squared t. In our second statement, our second parametric equation, we have y equals 4 sine t, and we'll need to go ahead and divide over that 4 before we can look at squaring this. Oops. Okay, and then squaring this gives us y squared over 16, right? Because we have to square both the numerator and the denominator of our fraction equals sine squared t. Okay, so now we're in a place where we can go ahead and utilize this identity, right? Instead of talking about sine squared plus cosine squared equals 1, we can grab our y squared over 16 plus x squared equals 1. And what we've done is we've come up with a rectangular equation that we can go ahead and graph. And this, for some of you, may not be the most enticing option as far as graphing goes, just because it does require you to remember how to graph in a lisp. In this case, we have a center at 0, 0. That's coming from the fact that this is the quantity y minus 0 squared, and this is the quantity x minus 0 squared. Okay, so that's where our center is coming from. And then we have a vertical radius of 4, and that is coming from the denominator here, the fact that that is 4 squared on the y, underneath the y. And then we have a horizontal radius of 1, and that's coming from the fact that x squared is being divided by 1. Okay, so I'm going to go ahead and start organizing this information graphically. The center at 0, 0, we'll go ahead and just maybe make note of right now, but I'll erase it here in a second because it's not a point of our function. But we have the center at 0, 0, we have the vertical radius, so we should have a point at 0, 4. We have the horizontal radius of 1, so the point 1, 0, another vertical radius, so 0, negative 4, and then the horizontal radius of negative 1, so we have that point there. Okay, so again, I'll go ahead and just take out that center point. And so I need to think about connecting these 4 points in the shape of an ellipse. And then we need to decide the direction in which we plotted these. Okay, so doing that will actually cause us to look at our t values, right? As t goes from 0 to 2, what direction are we traversing? And you can see that if you plug in 0 for t, you're going to get the xy point, and this is kind of done, just kind of doing this in my head, but it is kind of hinting at that table that we could have created to start to plot this. So when t is equal to 0, we do get the xy point of 1, 0. And then when t is equal to pi over 2, we get the point 0, 4. So what that tells us is we started over here at 1, 0, and our next point that we plotted was 0, 4. So we're working our way around the ellipse in the counterclockwise direction. So in order to communicate that, we'll put our directional arrows on there in the counterclockwise direction to complete our graph. Okay, so a little review on graphing conics there for you guys. Okay, B is again two trig functions that I think it would be interesting to go ahead and manipulate so that we could use the Pythagorean identity and try to write a rectangular equation as well here again. So we'll go ahead and look at x equals 3 plus sine t. And notice that instead of multiplication by a constant, we have an addition. So we'll have to go ahead and isolate the sine function. We'll end up with x minus 3 equals sine t. And then here we're able to go ahead and square each side to find that x minus 3 squared is equal to sine t squared. Okay. And then in our y equals 1 plus cosine of t, we'll do something similar. We'll subtract over y minus 1 to get cosine of t, and then we will square both sides here, and we'll find that y minus 1 squared is equal to cosine squared t. And this again allows us to fill in the Pythagorean identity, sine squared t plus cosine squared t equaling 1, right? Where instead of writing sine squared t, we're going to grab x minus 2 squared, right? We'll make that substitution. And then also instead of writing cosine squared t, we'll grab y minus 1, that quantity squared. We'll make that substitution. So that's telling us that we're going to go ahead and need to figure out how to graph the rectangular equation x minus 3 quantity squared plus y minus 1 quantity squared equals 1. And this is maybe a little bit more friendly than part A because this is simply a circle, okay? This is a circle with center 3, 1 and radius 1. Okay, so we'll go ahead and organize that information on our graph. Our center, we'll just kind of put as a placeholder, our center is 3, 1, and then we have a radius of 1 building around that, okay? So again, I'm going to erase that center because it's not part of our function, but it's helpful information to help us graph. And then I'll go ahead and fill in this circular shape. Now, the last thing that we need to do is determine the direction in which we plotted things. So again, kind of utilizing that tabular idea, thinking about, okay, well, when t is 0, right, that lowest value of t, what is my xy point? So plugging that into my functions, I'll find that t equaling 0 gives us 3, 2. Okay, so it looks like we are starting up at this top point on our circle. And then when t is equal to pi over 2, we get the point 4, 1. So we're actually moving in this direction. Okay, so now we're moving clockwise around our circle. So we'll go ahead and finish our graph by filling out that information, right? Placing those direction arrows to show, hey, we started here at the top and then we moved over to 4, 1, down to 3, 0, and around to the point 2, 1. All right. And this last part of this video is graphing part C. And notice part C is an absolute value equation as well as a linear equation. So it's a little bit different than our functions we were dealing with above. So I'm not actually going to try to fit that Pythagorean identity kind of skeleton here, right? I don't have a sine squared or a cosine squared. We could try and manipulate this into a rectangular equation, but the manipulation that's required with this absolute value is a little bit tricky. So I'm actually just going to go back to my kind of standard way of plotting these functions. I'm going to go ahead and build a table of values. So we know that we need to start with values of t, and then plug that into our x equals absolute value of t minus 1, as well as the equation for y, which is negative t plus 2, and collect those answers, those outputs, as our xy points that we can plot. So notice that your range or your domain on t is negative infinity to infinity. So we have to be a little bit thoughtful in the points that we choose. Okay, so if I just go ahead and plug in negative 10 for t, I'm going to find that that's the absolute value of negative 10 minus 1, which will be positive 11. And then over here we have 10, negative 10, which would be positive 10 plus 2. So it's going to give me the point 11, comma 12. And when I look at my graph, I'm not really set up to plot that, right? I would have to go pretty far off my graph up here, and that's going to be pretty difficult to recognize the shape. So if you ever pick a t-value that doesn't quite fit your grid or isn't super helpful in starting to see the shape, just back up and try again. So negative 10 seems a little bit too large. So why don't we try negative 3? So if we do negative 3, we'll get an x value of negative 3, oops, not t, negative 3 minus 1, which equals 4. We'll get a negative 3 plus 2, which is equal to 5. And that gives us the xy point 4, 5, which is a little bit more manageable to plot. So we'll go ahead and graph that 4, 5 on our grid, right? And you can see that that's a little bit more helpful than 11, 12. Okay, so next let's go ahead and grab negative 2. Plugging in negative 2 will give us a positive 3 as well as a positive 4. So we have the point 3, 4. Plugging in negative 1 will give us, let's see, negative 1 minus 1 is negative 2, but the absolute value of that is positive 2. And then we have negative 1 plus 2 would be 3. So we have the point next, 2, 3. Plugging in 0, we'll see that our point is, let's see, 1, 2. And then plugging in 1 to both of our x and y equations, we get the point 0, 1. Plugging in 2 will give us 1, 0, and plugging in 3 is where I'll end because it gives us that symmetry, right, of where we started. We started at t equals negative 3, t, and then we'll end at t equals positive 3, just to kind of give some nice symmetry on our graph. That will give us the point 2, negative 1. Okay, so we'll go ahead and finish plotting these along with that point 4, 5. So next we have 3, 4. We have 2, 3, 1, 2, 0, 1. And then we're changing direction here, right? Now we're building to the point 1, 0. And then 2, negative 1. And that pattern, that slope of 1 will continue. So if we want to fill in a couple more points, that's totally fine. So here we have the shape of our graph of these two parametric equations in our rectangular coordinate, and we now just need to add the direction. So remember that we went we started here at 4,5, and then we plotted down towards the y-axis and then down off here towards negative infinity. So we'll just add our directional arrows to this graph to show that we plotted it in this direction. One last thing that I want to mention is because we have this infinite bound on t, we'll have a corresponding infinite bound on our graph. So we'll be able to say, hey, we can continue off forever in this direction, right? These points, they'll continue plotting up here, and these points over here will continue plotting in this direction. So it's okay in this case to have arrows at the end of our graph.